Hello and welcome to the Weekly Space Hangout for Wednesday, December 5th, 2018. I'm Morgan Renberg, and once again, Fraser is gone. He's off swimming in volcanoes in Hawaii, I believe, which
I
is
hope
just the
he's
sort
not
of
swimming in the volcanoes.
thing. You
We
have no
want him to
sense of
come
fun.
back. We
No
really
sense of
do.
fun.
I have a
But
sense of fun.
joining me this week, as always, from EOS Magazine is Dr. Kimberly Cartier. Hey, Kimberly.
Hey, Morgan, happy podcast day.
And joining us from like the bottom of the world
Mm.
is Dr. Paul Matt Sutter, where apparently it is very hot right now.
Yes, I'm in
Where are
Santiago,
you?
and I'm in Santiago, Chile, and I had to flip my video upside down so that you could see me upright.
You look very
Thanks.
fine anyway. And filling in quite ably for Fraser tonight is friend of the show, Dr. Pamela Gay. Hey, Pamela.
Hey, Morgan, how are you doing?
I am wonderful. It's a Wednesday. We're doing the Weekly Space Hangout. What more could be better? We don't have any books to give away today, but we do have some great stories to talk about. We're going to talk about something called negative mass. I don't think that's a thing, but Paul's going to tell us. We're going to talk about OSIRIS-REx arriving at asteroid Bennu. That is certifiably awesome. I'm going to talk a little bit about gravity and time and what they mean. And Pamela is going to tell us about something. I don't know what story you finally decided to do, but it's going to be amazing.
I
But first, we're going to spend a little bit of time talking about money and
Yeah.
paying for things and science and how science isn't free and isn't done for free. And we need your help to make sure that more science is happening. So, Pamela, can you kind of fill us in on what's going on?
Okay, so this is best described by a shirt that I'm not wearing that says, "Damn it, Jim, I'm a doctor, not a fundraiser." But unfortunately, because I'm principal investigator, which means I'm the person in charge of finding the money for a lot of different projects, I go through life fundraising. And our team had thought we were finally good. We started off in 2012 with a large NASA grant that would allow us to build CosmoQuest. We had also diversified our funding, getting a variety of different contracts from different missions. Sequestration came. We lost most of our mission funding overnight thanks to Congress's mandated cuts. The problem is when Congress mandates cuts, you can't cut the budget of a spacecraft. You can't reduce the electrical bills. All that hardware and software fees, they stay the same. So the places that you have to cut funding are in the grant-funded projects, in things like what I do. And so we got cut. But we kept going. We did 2 different big fundraising events, Hangout-a-thons using Google Hangout on Air, and we raised enough money to make the difference that allowed us. We had to cut back some of our students. It worked out that the numbers graduating compensated for the decrease in our budget. We lost Nicole, who went and got a tenure track job in New Hampshire, and we kept going. Then in 2015, we got a huge new NASA Education Cooperative Agreement. But in the years since then, NASA's been told to de-emphasize how they do education. We went from being the NASA Educational Cooperative Agreement to being a Science Activation Cooperative Agreement. We've seen new laws pass on how citizen science is to be done. And then we've seen this big, awesome telescope sitting in the corner sucking in resources, and that's James Webb. And we started to get hints back in August that, well, James Webb didn't launch. There was going to be a $0.8 billion cost overrun, and there would be cuts. And NASA doing education still wasn't a priority. And while citizen science isn't really education, that's where we got grouped in. That's where our funding was put. So we were also told that they were looking to change how citizen science at NASA is funded, moving it out of education and putting it back in all the different sciences where citizen science projects get judged competitively side by side with science projects. And we have hints that if all goes well, there'll be a new call for proposals coming in February, asking people to propose citizen science ideas. The problem is that I found out at the end of October that all of our funding to do citizen science was getting zeroed all the way to zero. And this was happening at the same time that I was moving institutions to the Planetary Science Institute, which is an institute with over 100 PhDs doing cutting edge research, working on mission after mission after mission with top-notch people doing science education, with people like me who are crazy blended individuals. Some of my heroes are there. William Hartman with all of his art, David Grinspoon, they're all at this institution. So in 1 week, I went from on Tuesday putting in my resignation, knowing that my new boss would be talking to NASA on Friday, to on Thursday finding out all my funding was zeroed and having to figure out how to get all of my fundraising efforts set up at a new institution that I'm not yet working at. So that's what I spent the entire month of November doing, working 2 full-time jobs to get things going. And I'm now here to say that without your help, I have to fire every member of my staff January 1, which means that I'll be giving them notice pretty much Christmas Day. And I don't want to do that, knowing that there's this call for proposals on the horizon, knowing that I've always been able to get grant money in the past. And so I'm asking everyone out there one more time to, well, if you've ever said we need more money for science and we need more money for education, this is your chance to put your money where your heart is, where your ideas are, and help me. And the way I'm contributing to this is I have a husband with a good paying job, and I'm not going to pay myself one dime except out of grants. So if I don't bring in grants, I don't get paid. We're looking to raise funds strictly to pay all the rest of the staff who make CosmoQuest happen, the student programmers, the early career programmers, the science education researchers who are also students mostly. We have a really young staff, and then we have some fabulous people who have kids, Nancy, Susie, Big J. I'm trying to figure out how to bridge pay until we can get that next grant, now that we're in this awkward hole as NASA restructures how it does citizen science again.
One of the things that I've always found most attractive about astronomy is that it has this opportunity to be participatory in a way that it feels like is much more challenging in other fields. It's hard to sort of do citizen science at CERN or something in a way that feels sort of meaningful. But in astronomy, there are so many amazing ways to participate in research that actually helps, that to me that's really fulfilling. And honestly, even though I am a PhD scientist, I still sometimes like click over to moon mappers and circle craters and things because it's just cool, and it's cool and helpful. But doing that really enables us to do a lot more science than we could do as individual researchers. But it doesn't come for free.
No.
It's much, much cheaper than hiring other scientists to do it, but it isn't free. And to lose that would be to set us back a really long way in terms of the advancements we're making in understanding things like the age of the solar system, which we measure from crater impact rates on objects.
And we have some really cool stuff coming out. We're currently in the process of training crater finding machine learning algorithms to finish off the moon for us, because the moon is really big, and the best resolution complete maps we have are at the 3-kilometer level for marking out where the craters are. With CosmoQuest, we're going down to 9 meters instead of 3 kilometers. But humans can only do that so fast. But by using the humans to train the algorithms, we actually have a chance of finishing the moon. We just finished off Vesta. We're going to be bringing online a brand new project to measure how glaciers in Nepal are changing, where it's actually Sherpa citizen scientists who collected the data. We're going to have people analyzing. It's data that's going to be used in combination with Landsat to look at how glaciers are degrading over time. And we're working with the OSIRIS-REx mission. It's our software that their team is going to be using in part to find the rock they're bringing back to Earth. We're right at the edge of launching all these amazing things. And to find ourselves at a brand new shiny institute that is such a great place for us to be, and have all of these things on the horizon and lose our funding all at the same time is just, I don't even have words.
So let's talk about how people can pitch in. What are we planning to do?
So we currently have a Hangout-a-thon, but on Twitch, because Twitch has slightly better interaction. We're planning it on Twitch. We're doing this December 22nd, 23rd, and depending on where you are on the Earth, starting to go into Christmas Eve. This, unfortunately, was the earliest date I could figure out how to get everything put together for. We have a Tiltify campaign set up so that anyone else who wants to co-stream and raise money through their stream for us can join our Tiltify team, help us raise money. We're also taking funding through Streamlabs. One of the oddities that we're dealing with is because we're currently funded by NASA, I'm not allowed to ask for money on CosmoQuest.org at all. So we're having to do everything through slightly different links. So everything is currently linked through Twitch. If you go to twitch.tv/CosmoQuestX, under the video player, you can find all the information with links out to everything that we're doing. And if you don't have money to give because you're busy buying Christmas gifts, I totally get that. We have to keep the people in our lives, especially the kids. They need gifts for Christmas to feel right. If you like anything we have a Redbubble store that has lots of amazing artwork by Austin Hinterleader. So you can get a whole variety of different spacey scientific things over on Redbubble through us. And really every little bit really matters.
I've been around long enough to remember the old Hangout-a-thons back when we were actually using Hangouts on air. And they were just so much fun. It's for a good cause and we raised good money and we kept citizen science going. But like when they're happening, it's just like this sort of crazy, silly fun. And all of these just a random, amazing people show up for half an hour here or an hour there. And you jump on and you just never want to leave because you don't know who's gonna appear 30 minutes later and what they're gonna be giving away. And it's
oh my God, we have so many
experience.
giveaways. So I am one of those people that gets Loot Crate, but doesn't understand all of the things that comes in the box to my house. So I took inspiration from a writer friend of mine, Starla Hutchins, and she gets Loot Crate too. And the things that she gets that don't belong to video games and movies that she loves, she gives away to people who are fans of her books to encourage them to participate. Well, I have been storing for 2 years all the random Funko Pops, t-shirts, random figurines, and other things. And we're going to be giving away multiple things every single hour of the Hangout-a-thon.
I'm really looking forward to it. I'm going to be, for part of it, home visiting my family, and I'm sure I'm going to be running away to peek up my phone and see what's happening the whole time. And it's going to be really a lot of fun. And I think you'll all see a lot of familiar faces there. I haven't even seen the the guest list, but just based on my experiences in the past, it's going to be all sorts of people that you know and love. Getting to sort of step outside the box, and we're not confined within our little windows of talking about space news for 45 minutes every Wednesday. But just kind of screw around and play games and tell stories and do weird things for a good cause. And if you can't do weird things for a good cause, then can you ever really do them?
And I do have a very young puppy. There will be a puppy cam. And every time we hit a major milestone, there will be giving the puppy absurd treats just because, as a reward.
The puppy
to
is
all
adorable.
Of us. The puppy
Just
is
going to say, the puppy
adorable.
is adorable.
She looks like a teddy bear.
Can you give us the Twitch address one more time?
Twitch.tv/CosmoQuestX. The X is for
All right.
science.
And can you give us the dates?
It's going to be starting Saturday, December 22nd, and running in to the earliest hours of Christmas Eve, Sunday into Monday. 40 straight hours for science of science.
All right. It's not going to be something that you want to miss. Well, thanks for joining us to talk about that, and for sticking around to chat about the rest of our topics. But I'm going to go to Paul first, just in case the internet at the bottom of the world falls out and we lose you at some point. I'm also just really intensely curious about negative mass and what that means. Can you fill us in?
Yeah, so there's this news story making the rounds that, if the universe were made of half normal matter and half negative mass matter, then you could explain both dark matter and dark energy and solve all cosmological problems now until the future. So, first question that comes up is, what the heck is negative mass matter? Like, it's weird to just think about. Like, imagine holding something in your hand that weighs negative 5 pounds or negative
it's like
25
would be floating away from sources.
Yeah. This is exactly the thing. Like, if you posit the existence of negative mass matter, like if you say, matter is like charges, where you can have positive and negative charge, you can have positive and negative mass, then two positive masses will attract, two negative masses will repel, and a positive mass next to a negative mass will actually move off in one direction.
Oh no, we weren't fast enough.
Does he have negative internet stream?
I think so.
Paul, come back to us.
I think the internet was like understanding how much I hated this story.
So what do you object to this idea? I mean, physicists love symmetry, right? We have positive charge and negative charge. Why can't we have positive mass and negative mass?
Because some things are just scalar, and that's okay. Oh, he's coming back.
I'm back.
Hey.
The negative mass man is trying to keep me down, as usual. But the truth will get out.
So Pamela was just saying how much she hates this idea. I'm getting the sense that you probably agree.
It's just unphysical. Like, you can say, like, maybe negative mass exists. But then you work through it and you say, it violates conservation of momentum. It violates our knowledge of relativity. It violates everything about inertia, like very well-tested, well-understood concepts about our universe. It just breaks. Plus, we've kind of never, ever seen it. Plus, we have no reason to suspect how it might be created through any reasonable physical channel.
So why are we talking about this at all? Like, what is it solving for us in the midst of breaking basic things like conservation of momentum?
Right. So a guy wrote a paper saying, oh, if the universe were half negative mass, then you don't need dark matter, you don't need dark energy, you get to solve all these long-standing problems in cosmology with one easy fix. The problem is, and the paper claims, oh, if you seeded the universe with negative mass, then all the normal mass would clump together in something you would call a galaxy, and all the negative mass would get pushed out in between the galaxies. And this would kind of, quote unquote, keep a lid on the galaxy so you can keep their rotation curves high. It would separate the galaxies from each other, causing an accelerated expansion of the universe. The challenge is that the paper doesn't actually show any of that, despite it being in the abstract. Plus, the biggest issue, one of many issues, is that there's more to cosmology. There's more to our understanding of the universe than rotation curves in galaxies and the expansion of the universe. There's also structure formation, the cosmic microwave background, baryon acoustic oscillations, Lyman alpha, nucleosynthesis. I could go on. I could write an entire book about it. In fact, I did. And if you want to explain something in the universe, if you want to explain dark energy, if you want to explain dark matter, you are welcome to it. Crazy ideas are more than welcome, but you have to face the challenges. You have to explain all existing data, not just some of it, not just the parts you like. You have to explain all of it. And if you can't do it, then you're not a viable cosmological theory. And that's it.
Larry Beckham is asking, does the math work, Paul?
No. In fact, there it is. The math simply doesn't work. In fact, the paper addresses this, saying, "Oh, we put in negative mass and regular mass, and then we ran the math. We ran some simulations that we cooked up, and we just kind of ignored this whole conservation momentum and inertia and speed of light business, just so we could run our simulations."
But that's not how science works.
Astro B is going, but is negative mass really antimatter? It sounds like it's not. A lot.
Yeah, I know. There's all these matter terms, which I'm going to blame the particle physicists for all this. There's matter, there's antimatter, there's dark matter, there's negative matter, there's exotic matter, et cetera, et cetera. Antimatter is just like normal matter, but with opposite charge. So if you take an electron, all the properties of an electron, and you flip its charge, you get the antimatter of the electron, the positron, but it still has positive mass. Everything in the universe has positive mass or positive energy.
We've talked a lot this year, I feel like, about what's science, what's not science, what's responsible science, what's not responsible science. Is there any value in your mind to publishing an incomplete incremental result like this before you've solved all the issues? Like you said before, if you don't have a real cosmological theory, if you can't sort of be compatible with all our past observations, it is the bar to publishing that you have to have already met all of those. Or can you throw an idea out there and kind of say, this is a starting point that we want to work from?
Yeah, that's a great point. And no, the bar isn't that high to publish. I mean, I've written a bunch of crap papers myself, so I'm not going to hold anyone to a higher standard than I myself have been published. There's a certain way to approach it. Like if you have crazy idea and you think crazy idea is going to solve some, long-standing problem in astrophysics, yeah, and you concoct a solution and you're able to solve that problem in a very narrow sense, it is up to you to at least sketch out how it might fit with the existing framework, how it might not break other existing observations in a very obvious way, and help and then guide the reader, other researchers, like, okay, it might solve this problem, but here's some ways to test it. Here's some other observations you might be able to make, or some lines we'll continue to follow. That's totally legit. This paper does not do any of that. And in fact, this paper very clearly shows in itself how negative mass cosmologies don't work, because they run a simulation and trying to generate structure formation, the cosmic web, the large scale structure of the universe, and they don't. They talk about the CMB, which would be a major test of this, because if negative mass is present in the early universe, you bet it's going to affect the cosmic microwave background and almost definitely break all known observations of it. And the paper doesn't address that. So the paper itself is not consistent with its claims.
Well, let's just leave it at that, I think. And
peace out, negative matter.
Move on to some science that is definitely real and very cool. And that's OSIRIS-REx arriving this week at Bennu. Kimberly,
yes.
You want to tell us about that?
Oh my gosh. This is a thing. This particular asteroid mission is a thing we've been waiting for the past 2 years since it launched. I'm clapping. Yay. So the OSIRIS-REx mission, which is a NASA mission, arrived at its target asteroid Bennu midday on Monday after 2 years and 2 billion kilometers of travel. And it arrived, got within about 19 kilometers of this asteroid, started taking really high resolution pictures of its surface. And if you haven't seen them, they're particularly stunning, I have to say. And it shows that it looks weird. It does. It also looks oddly familiar in that it's a very similar diamond shape to Ryugu and has very similar large boulder structures on the surface. I'm pretty sure that was entirely coincidental that these two asteroids that we arrived at in the same year look very, very similar, at least on the surface and from far away.
Kathy Q described it as a overly spiced crouton.
That's a very apt description. It's an overly spiced crouton. It's a diamond shape. And so what OSIRIS-REx is going to be doing is doing very high resolution mapping of the entire surface of Bennu and getting an idea of what the soil and the surface structure is like and the composition of the surface is like during its orbital phase, so that in its next phase, it can do sort of like a quick drop to the surface and try and grab some material to then bring back to Earth. And so all of this high resolution mapping that you're going to be hearing about in the next couple months is all to pick the best possible landing site for it to do a little hop down onto the surface and then scatter away and come back with some actual samples of this asteroid.
And this is what we're going to be doing over at CosmoQuest, and we're stupidly pleased about this. We just need to figure out how to keep everything funded until that happens.
It's always kind of funny to me when we go and visit one of these little objects. Like, this is a really small thing. It's 500 meters across. And so it's a couple square kilometers probably in surface area. And there are not many areas of Earth, a couple square kilometers in size, that will have ever been studied as closely as we're about to study this random asteroid in a solar system full of asteroids. And we're going to like overanalyze and overinterpret every little piece of this thing because it has to be representative of a whole class of asteroids that we will never go and visit. And that's just like a strikingly different way to do geology and planetary science than how we do it at the Earth, where we sort of look at everything in the whole planet and then say, okay, these are the truly unique and interesting things, and then go and visit those.
Yeah, it's one of the interesting points of trying to do asteroid science is that going to any one of these particular targets is incredibly time intensive, incredibly expensive to do. And we sort of know from remote observations of asteroids that there really aren't all the same. Like even within the same spectral class of asteroids, we call some of them, carbonaceous. We call some of them iron rich. We call some of them rich in organics or water or something like that. But even within a particular class of asteroid, there's an incredible amount of variety. And you're right. We're sort of saying, well, let's go to this one B-class asteroid like Bennu is. And that'll teach us about B-class asteroids, but we don't actually know if that's true or not.
It's like if you looked at one stream on Earth and said, this will teach us about all streams
This is how rivers work.
That's kind of the scale at which planetary science works. And only a couple of places in the solar system have really sort of escaped that level of generalization.
Mm-hmm.
And that makes each one of these missions really unique and cool. But also, I think we have to just sort of always keep that in mind, that we're looking at some tiny postage stamp piece of the universe, and it's sort of no more notable than that on the biggest scale.
And one of the things here that does make things at least a little bit easier is we do have Hayabusa 2 at Ryugu at the same time. These are two slightly different kinds of asteroids that are the same size. We're following up on the amazing data that we got from Itakawa, which was another one of these baby asteroids. So we're at this point where we've had Dawn doing this fabulous set of surveys of two paired rocks, Vesta and Ceres, that are big enough to be geologically structured and are inside and outside of the solar system's frost line. And now we have two different missions, Hayabusa 2 and OSIRIS-REx, that are going to two distinctly different but similar sized near-Earth asteroids, where we have one that's carbonaceous and the other that's a metal asteroid.
Yeah, and I think one of the other sort of lesser known aspects of OSIRIS-REx that I think can only be done at Bennu of the future upcoming asteroid missions is studying a really, and rare physical effect called the Yarkovsky effect, which can affect the orbits of asteroids and sort of slightly shift them out of their gravitational only orbits. And it has to do with how the surfaces of these asteroids absorb solar radiation, and then after it rotates away, radiates that heat off onto the cold side, and that radiation pressure slightly shifts the asteroid's orbit. And we know that with Bennu, at least, in the past 20 years that we've been intensely studying this asteroid's orbit, it shifted something like almost 300 meters in its orbit from where it should be. It's noticeable and it's measurable, but it's not a physical effect that we've ever really studied up close. And this is an incredible opportunity to do that.
And just to be clear, that's pressure from light.
Yeah.
That's
shifting a 500-meter hunk of rock.
A 500-meter hunk of rock in space. That's just really cool.
And
I mean, and important because, we don't want one of these hunks of rocks to hit Earth without us knowing about it ahead of time. We'd like to know if anything is going to shift things out of where we think they should be.
And Bennu is exactly where Bennu is supposed to be. That's just not where we thought it was going to be, because we don't fully understand this effect. And with an asteroid like Bennu, it's really important because there's a non-zero chance that this half-kilometer city killer of an asteroid is going to hit the Earth in the next century.
Yeah, I think it's something like 1 in 2,700 or something like that.
Non-zero, and we need to understand how it's getting pushed around by light so we can make sure it's not getting pushed into us.
So, Kimberly, can you kind of sketch out the mission timeline going forward? Now that we're here, what's going to happen and when?
So we are here at Bennu, what I mean is that they've officially called it, they're on target at 19 kilometers away from the asteroid itself. And from now until the end of the year, they're going to be slowly getting into orbit around the asteroid, and they expect to actually get into a very close orbit at the very last day of the year, December 31st, so that they can do lots of flybys and get really sort of like skim the surface, get really, really close and map. And then they're going to, I think it's about a year and a half from now, they're going to officially attempt their first drop down to the surface. And they hope to be back with a sample by 2023.
All right, well, that's...
So 5 years from now, we may have a sample of this asteroid in hand, or in lab, I should say. Probably not ever going to hold it in your hand, but
well, that'll be here sooner than we know it, with a lot of cool milestones along the way.
So congrats, OSIRIS-REx.
Hooray!
Yay! That's already worth it, I think.
All right, let's shift gears, and I want to talk about time and gravity. And a
Is
couple
it
weeks
wibbly
ago,
wobbly
it is timey-wimey and wibbly wobbly. Um,
stuff?
and a couple weeks ago, we were talking at my behest about the kilogram and how we were redefining the kilogram in terms of fundamental constants and forces of nature rather than random objects stored in bank vaults. And the idea of time and atomic clocks sort of started this whole process back in the 60s when they first started making these clocks and realized, hey, we can measure time based on something that happens totally normally in nature, which is watching electrons change energy levels within different fancy atoms. And they bounce up and down between their energy levels at very, very, very predictable and repeating rates when you shine light of certain colors on them. And the last 50 years has basically been finding new elements to shine new colors of light onto that make more and more accurate clocks. And we've kind of hit the end of the line with that because the National Institute of Standards and Technology here in the United States, which is basically in charge of measuring stuff, has created an atomic clock based on yttrium that is now more accurate than our understanding of Earth and Earth's gravity. And that's just crazy.
So what does that mean? We talk about gravity, but like, what?
Yeah, so this is where it gets kind of weird. So Einstein's relativity tells us that time runs at different speeds depending on how close or far you are from stuff with mass. And really, we only care about big stuff with mass, of which the Earth is pretty close to us because that's where our atomic clock is sitting. And every sort of like meter you climb higher above the Earth, you're experiencing a little bit less gravity from the Earth. And therefore, time is running at a slightly different rate for you. And so this clock basically is so sensitive that the largest term in the uncertainty of its time now is its position above the exact center of the Earth. What we call sort of its, so we measure the surface of the Earth with what's called a geoid, which is a sort of idealized one step above a sphere, this idealized idea of what the Earth looks like. And then every point on Earth is some distance above this sort of like theoretical surface. And you can think of this surface as basically sea level. But it turns out sea level is not always at sea level. And that's kind of part of the problem here. And for any given point on Earth, basically, we can figure out using science how far it is above or below the geoid to sort of plus or minus 90 centimeters. And so where we are with this clock is that the thing that is confusing us about the rate at which it's ticking is where in that 90 second or that 90 centimeter band it actually is. And this clock is so accurate that it would be sensitive to changes in height of 1 centimeter. So basically 100 times better than we can measure is what it's sensitive to. And so it doesn't matter how much more accurately they figure out the mechanism of the clock until we can know where it is more precisely. And scientists being awesome, they have already sort of figured out how to turn this into an experiment. And the idea is to build a bunch of these super accurate atomic clocks and put them all over the Earth and basically flip them around and use time to measure the gravity of the Earth. And so we will understand in some number of years how the mass is distributed within the Earth, which is what gives us the shape of the geoid, entirely based on how fast clocks are ticking at various points on the Earth's surface. And that's this is where it gets very weird. And metrology is a weird thing. And when you start thinking about like whose time is right, that's kind of where the problem is. So the GPS is what gives us this plus or minus 90 centimeters accuracy. And so the idea here, I think, is basically to build a bunch of clocks in the same place and then move them to different places in a way in which you can sort of keep track of the accumulated relativity change, acceleration, deceleration that's happening, and then bring them back together and see how they compare, and then sort of map out the gravitational potential paths that they must have taken through space-time around the Earth to make that journey. And
That
that's
is
just
insanely
weird.
cool.
It's so cool.
John Jorsk is saying we need to put a clock into a stable orbit around the sun. I mean, imagine if we could be able to like measure mass movements of like Mercury coming nearby and things like that.
Yeah, that's what relativity basically promises, is that if you can measure mass, you can predict time. And if you can measure time, you can predict mass. If you can predict math, you're pretty magic. And it's just really cool to think that for centuries, we've been restricted in one half. We can measure time more poorly than we can measure gravity. And now suddenly we've passed this threshold where we can measure time more accurately than we can measure gravity, and we can start attacking all these problems from the other end and kind of work them back in the other direction. And who knows what kind of new approaches that will lead to.
So in the past few years, there have been quite a few advances in the technologies that lead to laser altimetry and LiDAR and things like that seek to map the altitude of every little point on Earth as accurately as possible. And there's been some great advances in that recently. So I guess my question is how certain are they that we're not going to figure out the problem from that angle before we are able to mass produce these atomic clocks and do all of these fancy gravitational experiments?
Yeah, this is where it kind of gets subtle, because I've been sort of mushing together different ideas of height. And so what a laser altimeter measures is what we call geometric height, which is sort of physical height in a given place. What these clocks measure is what's called geopotential height, which is basically the height along equal paths of gravity. And so an altimeter can tell us the physical shape of the Earth. A geopotential measurement will tell us the shape gravitationally of the Earth, which will tell us about the relative positioning of stuff inside of the Earth.
So this will take care of things like different compositions or different densities of materials distributed throughout the mantle and the core and things like that.
Right. And so they're kind of complementary measurements. If you don't know at all the physical shape of your thing, then a knowledge of its gravitational shape might not really be that interesting. But if you know the physical shape, then you're kind of nesting that gravity inside of it, and that lets us, we know there can't be mass of the Earth 1,000,000 kilometers away, because that's not physically where the Earth is. And so it starts to constrain the problem when we start sort of removing all of these solutions. We know that all the mass of the Earth isn't exactly at the center of the Earth's core because we're standing on the surface. And so we can eliminate that solution. And we can eliminate the solution that has mass where the moon is. And we can start eliminating those arrangements of mass and then kind of work our way closer and closer to the true shape and true distribution of what's inside Earth without ever actually seeing it. And that's just awesome.
We're getting a whole bunch of questions that basically boil down to, and gravitational waves. Can you detect them in any way if you put them in an orbit, if you just leave them sitting there? Are these things potentially a LIGO replacement?
I have no idea.
I don't either.
I truly don't. You would think that in principle you could do it, but then as we've learned with LIGO, what's true in principle isn't always easy in practicum. And so I think LIGO and LISA, the space-based future of LIGO, is probably our best bet for now. And I don't know if that's segueing into what you wanted to talk about at all, Pamela. But if not, we can chat for a minute about awesome new discoveries of gravitational waves.
So yeah, there was a conference last weekend out at University of Maryland where they brought together a bunch of the folks that are working with the LIGO system, with the Virgo system to detect gravitational waves. And on the Saturday of this 2-day conference, they released a catalog based on reproducing all existing LIGO and Virgo data using their better understanding of what gravitational waves look like in the data. They reprocessed everything and they were able to recover 4 gravitational waves that they hadn't even seen before. And they've now increased the known suite of different combination of black holes coming together. We still have the one neutron star collision. And in one instance, they were able to recover the furthest out black hole merger ever seen. It merged into a system that resulted in an 80 solar mass black hole, and in the process transformed multiple solar masses worth of energy into like energy. So in the process of merging, not all of the mass goes into the result. You don't take 240 solar mass black holes and end up with an 80. You take 2 that add up to a number greater than 80, and then all that extra mass becomes pure energy, light, gravitational waves. In this case, the gravitational wave energy alone was roughly 4 solar masses.
It's so weird to think about just like matter disappearing from the universe to become these wiggles in space-time. So this brings us up to 11 detected gravitational waves, right? I think that's right.
It's
Does
10
it
black
go
hole
up to
black
11?
holes. It's 10 black hole and 1 neutron. So 11 total gravitational waves.
Yeah, and to think that like 2 years ago we were talking about could LIGO even detect anything?
Yeah.
Was it kind of time to give up on that idea and go back to the drawing board?
And now we have enough to put into a catalog. How cool.
I'd
A
say
small
a table.
catalog, but
It's a table.
it has
Hey,
potential.
a table is a form of catalog.
It has potential. It has room to grow.
It's cute.
So how many of these things do we need before we can like start doing meaningful statistical interrogations
1,000
of what's happening? 1,000, you're saying, Paul?
plus or minus 1,000.
Well, we're at the minus.
Yeah.
At the bottom end of that.
Right now,
So
we're kind of
does that seem like a long way away or relatively close?
Well, hey, if it turns out you can double your number or roughly double your number of detections just by combing through the data again, do it again. Maybe they'll come up with another dozen.
Hey, it worked for Kepler.
Yeah.
So do we think that, in the next 10 years, we will be able to find 1,000 with current technology? Or do we need LISA and other next generation solutions to get sensitive enough where the rate of mergers is high enough that we can detect them?
Well, it's not just the rate. It's LISA's going to be able to detect completely different kinds of gravitational waves, different energies, different masses being combined. There's only so many of these things to detect. So yes, it's going to take additional instruments that further diversify the space that we're being plotted, which means you actually need to get an even bigger sample so that you can well sample the entire diversity of the parameter space. And then you just have to wait for the stuff to do the merger thing.
So you're saying it's hopeless. We should just give up.
It's not hopeless, but it's a get off my lawn. This is science for the kids to do.
But it is crazy. It's crazy. We weren't expecting even this high of a merger rate. Like LIGO team wasn't expecting another detection for another decade. But it turned out that there is a certain class of black holes that merge with a certain enough frequency that we can detect it.
So do we have to go back and reevaluate our cosmology to kind of explain where these guys are coming from and why they're, getting busy so often?
It's not so much our cosmology as, I don't know if initial mass function is the right phrase either, but that thing that generates the 20 to 40 solar mass black holes. There's more of those suckers than we'd previously thought. So it's the masses at which stars form, the rates at which stars merge to get to these.
So this is like a problem for
weird
stellar
weight objects.
Yeah, this is a I would classify this as an astrophysics problem, not as a cosmology problem. That is not a downgrade. That is just it's not a
Sideways.
necessarily it's a sideways thing. Thank you,
Yeah.
Pamela.
All right, well, let's wrap it up there, I think. What a great note to end on. Paul, I'm going to let you go first. Why are you in Santiago, and what are you up to?
I am in Santiago, and I am down to exploring the because I'm bottom. Never mind. I'm going to explore the Atacama Desert. I'm here leading an astro tour with 22 of my closest, dearest, best friends in the world. And we're headed up to the Atacama to San Pedro here in a couple days. And we're going to spend a week at a resort soaking in the night sky every single night and then going to explore the alien-like world of the Atacama Desert.
Have fun in Mars.
Jealous.
I will. Yeah, you should be jealous.
I am jealous.
Kimberly, what are you up to?
Well, I'm getting ready for this fantastically big meeting of geoscientists and planetary scientists called the American Geophysical Union Fall Meeting 2018, which is run by the same company that runs my magazine. So I am knee-deep in all of these planning efforts. And so next week, you should be able to have wonderful new geoscience and space news every single day, including very cool things about Mars and OSIRIS-REx and Hayabusa and all of the other fun things.
Where do we find that stuff?
You can find all that stuff at eos.org, and also at news.agu.org.
Pamela, what are you up to?
I am getting ready to go to the AGU meeting where I will be producing the Daily Space every day at 1 p.m. Eastern, unless I get consumed by the internet. And I will be bringing you all of that cool news that Kimberly is helping to make happen. When I'm not putting together the posters that our team is going to be having up, I am working on planning the Hangout-a-thon. Check it all out at twitch.tv/CosmoQuestX, where we do the daily news Monday through Friday, 1 p.m. Eastern. If it's not me, someone else will be there hosting, except on holidays.
And I am also going to be at AGU next week. And
Man, I'm the jealous one now.
Fraser is in Hawaii still. And so all of this is adding up to the fact that there will not be a weekly space hangout next Wednesday, December 12th. So don't burn your iPhone down in protest. We will be coming back the following week and are planning to take off no more weeks for the rest of the year. And so just hang on for one more week. Tune in to all the great content that is going to be coming out of AGU because it's going to be amazing. And we'll see you in 2 weeks. I'm Morgan Renberg. Thanks to everybody. Good night. Good morning. Good afternoon.